And we're live. So let's see if we have any sound. Let's test sound first. And yeah, seems that worked. Okay, so today's lecture is test effort assessment. And okay, that means how can we know that developers are doing a good job testing the software? So we are trying to put a quality measurement on the testing effort. So testing itself is a quality measure of the code or of the system code, but we want now to understand how well is the testing done. So this is something that I hope that you've recognized from before. This is the requirement pyramid. And if we start up here in the needs, you can see that there are some clouds up here. These are fuzzy requirements. These are the needs of a customer, the need of someone who needs our system, right? So, and the needs are clouds because they are fuzzy, because they are ideas. They are abstract concepts in head of someone. These needs can be put down as features. And with feature here, I mean something a bit bigger that we formalize for a system. So in the example that I have, we have a need that in a web application, we only need some people being able to log into that web application. So we have a need for a secure authentication system. So, and really the idea or the need of the customer is that some people are going to be able to access the system and other people are not going to be able to access the system, or that we have parts of the system that a certain group can access privately. So the feature for that need is going to become an authentication system. And the feature could be, I mean, with feature is just a high level requirement in this case. So usually one single feature can be divided into several use cases. So you can see that the feature up here has several use cases. It may be that we have different features, like in a web application. We could also, the web application could also have a system where we can, have a, if it's a web shop, we could have order system that is connected some way to the authentication system, so they can share use cases. So on the next level in the requirement pyramid, we have use cases, and you've probably written these or at least heard about use cases before. So I'm going to read a use case here. It's not very detailed. A use case, just a reminder, use case is like a dialogue or with the system and its users. And this is a use case for logging in. So user wants to get access to restricted wants to get access to restricted access. Maybe that should have been rephrased. User requests access. System asks for credentials. User gives credentials. System verifies credentials and present restricted access. So this is the classical login scenario. So so the first sentence here is just the need of the user to get access to a restricted part of the system, and then we ask for that. That in itself, when we ask for logging in, that is usually from on my phone. If I open the phone, it is not logged in, and I automatically gets this question for access by just starting up my phone. I get it. In a web application, it might be that I can browse the web store without logging in, and then I need to request access by pressing I want to log in. When I press the I want to log in, system asks for credentials. That could be happening in many different ways. So on my phone, I have a camera on the phone, and it automatically logs me in if it sees my face, if it recognizes me. So, but in a web application, it could be that a form comes up. It could be many different cases where or it could be implemented in many different ways. And then user gives credentials. Depending on the way that the system asks for the credentials, it could be implemented also in many different ways. User gives credentials, and then system is verifying these credentials, checking these things, and presenting the restricted access. So as you see, this is very abstract. This use case is written in a very abstract way. So it is not connected to any specific implementation of authentication. And this is the way that we want to write our requirements, usually in the beginning at least, in order to give a wider range of possible implementations, so that we can have some creative freedom as developers. And this could mean the usual login system where we have a form with a field for username and a field for password. But this could also be a camera that is automatically logging us in. This could also be implemented by people. So when you're going to a bar and there is someone that checks your identity, that you're old enough to get into the bar, that is actually the same use case. So they are asking for your credentials, you pull up your ID card, they are checking your ID card, and then they give you access or they deny it. This could also, when I was going out, we got these stamps. I don't know if that is done right now also, if you're paying to go into a disco or something like that. We got these stamps, and suddenly we have some kind of temporary, the stamp is like a temporary user credentials. So it is, my ticket or so. So if I go out for smoking, and then I can, use that in order to get in again. We can have many different implementations for this. Okay, so this is a use case and how it's written. And then we have an alternative scenario. So that if the user gives invalid credentials, the system presents that the credentials are invalid. And usually we also have like a loop back into the, or we could have a loop back so that, okay, I need to pull up some other credentials. So maybe the stamp has faded, and then I need to show my ID card again. So on this use case level, you can see that there are use cases, and then from the use cases, we have scenarios. So each use case can result in many different scenarios. So we have the main success scenario is when we are provided access to the system. So we present the correct user credentials and we get access. An alternative scenario for the same use case could be the alternative down here, where we don't get access. And then you can see that these scenarios then can result in several test cases. So for the main success scenario, we could log in given correct credentials, of course, or we could log in using the temporary credentials, the stamp on the hand. So if we have this more complex logging in system with different means of logging in, of course, we need a test case for each type of logging in. We could also, need different or motivate different test cases for the same scenario by just having different test data. Let's see if Daniel can log in, and let's see if someone else can log in. So we have two scenarios just to make sure that it works. No, one scenario, two test cases, two different users, and we try their credentials to log in. The same way, and perhaps more important might be to check the alternative scenario. So the reason that we don't get access could be manifold. So here are different scenarios for logging in. Some of you might recognize these. So we have different test cases for logging in scenario. And the first one is just to navigate to the page, just to divide the test cases into different parts. And then we have failed login without entered any fields. So that is the alternative scenario where we don't give, we actually don't give any credentials, but we call that invalid credentials. And then we have failed login with only username, so no password is handed over. And then we have a third test case on failed login with only password but no username. And then we have failed login with wrong password but existing username, failed login with existing password but wrong username. And then we have, finally, we have the main success scenario. Success login with correct username and password. And then we're also making sure, because now this is a web application, so it can be reloaded. We can press F5 or Shift F5, or we can mark the URL in the browser and press Enter, and now it's going to be reloaded. So we must make sure that we are still logged in after reload. Yeah. And we can also check that we're logged in another window and stuff like that. So an interesting thing here is that the use case is very abstract. It's not written to any specific implementation. It should not be written to any specific implementation. So we're not locking a use case to a web application, for instance. We might want to do that, but then we are limiting the solution space for our developers. So if we are locking into a web application, maybe they can no longer do an application for a mobile. Yeah. Okay. So did I do a good job testing this? How do we know? In order to know, we want to know, are there any more scenarios? Are there any more cases? If there are more cases or more specifics that we need to know about, then we would like test cases for those also. I get the question, are you always running the test 1.2 to 1.6? So every time I change my authentication system and I release a new version of the authentication system, I should run all the test cases for that system. Normally, that could be very boring. Running these test cases, I'm just going to click on the link and we can, see the different test cases. So we have this failed login without any entered field is not as bad. You just, make sure that both the username and password is empty, and then you press login. So it's quite easy. And we make sure that not logged in is shown, right? But now we're going to test cases where we need to input stuff. And this quickly becomes boring. And when it becomes boring, we don't like to do it. And then we don't want to do it as often. And then we, also cheat a little bit when we are doing it. We try to get away from boring stuff. So this should really be automated. By automating this, we can run it every time by making automated unit tests for this, or maybe we should not call it unit test. By making automated systems tests for logging in, we can run them often. So yes, you should rerun these every time you release a new version of the system. We could, accidentally introduce a bug that allows people to log in. So we should try all the failed cases every time. But that said, maybe we are releasing a new version where the only thing that we change is the CSS. So we're only, tweaking some appearances, and then we are deciding, okay, we're going to check the login form and we're going to run one of the failed cases just to make sure that the error message is also visible still. And then we're satisfied with that, right? I got a question. Is that both client and server side? Yeah, sure. So the ideal case is that we always rerun every test case that we have. But the ideal case demands that we automate these test cases. So in order to automate these in the browser, we probably need a browser plugin that can, put text in an input box and press the login button for us, and also check the results. And there are these plugins for the browser. So we have, I think it's called Selenium web browser, where we can Selenium web driver or something like that, where you can create these test cases so you can automate those. Okay. So I asked the question, am I doing a good job? And the real thing is that we cannot see it just from looking at the test cases themselves. We can say, oh, they are many. Oh, there's a test case that I didn't think of. But really, we need some help. And a test traceability matrix is a way of, trying to at least make sure that we have test cases covering different requirements. So we can see that the requirement 1, this probably what they mean. I just taken this picture from the Wikipedia page. So I'm assuming a lot here, but let's say that requirement 1 is that we have an authentication system. And then we have different use cases, use case 1, use case 2, use case 3, and then we have some technical requirements also connected to the authentication system. And then for the use case 1, we can see that we have 3 different scenarios for use case 1. So requirement 1, use case 1, scenario 1. So that could probably be, the main success scenario. And then we have some fail scenario and some fail scenario. And then, so these numbers of the use cases are connected to different use cases. And then the second number is the scenario number. So the bad or the good thing with this number system is that it's very compact, so we can have this matrix. The bad thing is that we need to unlock the secret of what these numbers mean. Here we have test cases, 1.1.1, 1.1.2, 1.1.4, and stuff like that. And these test cases might have a similar naming strategy. So the usual naming strategy that I would have would be requirement, use case, and then test case number. I don't know how they did it here. It's a bit confusing, but what we can see in this matrix is that we have 3 tests, this test, and this test, that is covering a specific scenario in a use case. So test traceability matrix, we can just check up here how many test cases there are for each scenario. So this at least gives us some idea that, okay, we have covered all scenarios. But behind this, there is the question, is there a scenario that we have not yet thought of? Or are there, for this scenario, a test case that we didn't think of? And this is, we still need to think about this. We still need to work with the requirements. We still need to, sit down and work with that. So it's quite hard to find a missing requirement or missing test case. Okay, so for manual test cases, or even if we automate this, we might want to do this test traceability matrix in order to show that, okay, for all requirements, we have test cases. What about unit test suites and how to assess them? And for manual test cases, this is as far as I've gone. There might be other things in how to handle it, but I'm not sure. Okay, so for unit test suites, how do we assess them? So we're going to take a look at a test suite or a program called YodaTime. And this is a module for Java for handling time. So it's a quality replacement for Java date and time classes. It allows for multiple calendar system, and it has, all these different calendars. So we can translate the date from our calendar system to other calendar systems. It has a lot of different, we just go into the code a little bit. Or maybe it's down here. A lot of different classes. There are so many classes in this one. Chrono. Okay. So trust me, there is a lot of code in this project. And you can see that it's has been pretty intensely developed. So there are 2,271 commits. There are, let's see, how many people are working with this? 90 contributors that have been working with this project for a long time. And how do we know that this is good, well tested, that it works? Yeah, let's check if they have tests. So I would say that is the first thing. So let's go into this folder. We can see that there is a test folder, and then we can see test classes and test classes and test classes and test classes, format test classes, TZ test classes. Okay, good job. I trust them. Do you trust them? So if we go into one of those class load tests, okay, there are a lot of print statements. I wouldn't have print statements in a test, by the way. This is just a static main. I'm not sure what this is. Let's go test fixed date time zone. So we can see that these are test cases. They have different suites. They have different asserts. Is there a missing assert here? Every test case has multiple asserts. We don't recommend that either, right? Okay, so we can find some, some faults in the way that they've written the tests right here, but can we say that they have done a good job or not? A lot of tests. Good work. I trust you. Okay, so let's imagine that this code now is running in your self-driving car, and you're putting yourself in the back seat and you're instructing the car to drive you to the airport. You wouldn't trust it then, right? So we need something more. Okay, so let's see if we can find something more. So by the way, me doing this is also a way of, trying to show you how to work with this a little bit for assignment 2, right? Because it's about finding some open source project, and this is an open source project where they have some testing. And we've fulfilled the minimum requirement that for testing. We can see that at least this 3 months ago, the source code was updated. So it's also fairly recent. Maybe not the most fun project. I think it says that Yoda Time is considered a largely finished project. No major enhancements are planned. So it might not be, so up to date, really. But at least it has some documentation and stuff like that. Okay. So let's search for the word test. Unit tests are written in JUnit and part of the build and continuous integration. Okay, that sounds good. Changes via page pull request must include appropriate test coverage. So they have some requirements for testing this system. At least that to me sounds good and promising. So I after a little bit of searching, I went to their homepage. I checked in the bottom and I could find test results. So here is the surefire report for their system. So we can see that they ran 4,000 tests with 0 failures, 0 errors, and skipped 100% success rate. It took them 3 seconds or something like that. I'm assuming this is seconds. Okay, now you get in the back seat of the car. Now you know that all their tests succeed. We don't know what's in the tests, okay? So we can go a bit further and we can see that the different packages have a different number of tests. So this Chrono GJ only had 2 tests. Maybe that is too small. The other one, this one, has 3,000 tests. Sounds good. So the sort of level that we are here now is the sort of same level as we did here, right? We're just saying that yeah, we're actually missing that these tests are succeeding or not. We're one step ahead. Hang on, did I? So let's go back to that one, to the report. Okay, success rate doesn't give us all. Let's see if we can find any of the things that I wanted to see here. So I'm not used to this report, so let's just see if they can. So we can see the names of the tests, but that alone is too much information, and we need a lot of information in order to understand if there are missing tests, really. So the interesting thing would be if they have any more information that could give us an idea on if there are missing tests or not, right? So I was hoping that information would be here, but I don't find it. Okay, let's go back. So we are missing something from that. Just the test results are good, but we are missing something. Oh, %. Yeah, during system testing, we were going to talk to them about that. Okay, so what we need is to get what I call adequate tests. So adequate test means that we need a measure of what is good enough, what is adequate. And this could be different things. So let's talk about tests as constraints instead. So let's imagine that we can have all possible solutions to a problem. So we have all possible programs, but only some parts of those programs are solving our problem. So let's take something very, very simple, like the add method we had during the first lecture. So it added 2 numbers. We get 2 numbers in, it adds them together and returns the result, right? And all possible programs contains, Doom, it contains World of Warcraft, it contains any possible program ever written and all programs not written. And most of those doesn't solve the add problem. So imagine that we have a space of all possible programs. Some of these programs looks like the add program. I make them into a green cloud here. They are more probable. So World of Warcraft or any other game is not the add solution, right? So it's outside in the gray area. But The add program which I created for the first lecture, where we had a minus sign instead of a plus sign, more looks like the add program. It's actually even correct for all b equals 0, if you remember, because a minus 0 is a, which is also the same for a plus 0. So we have some reliability for these. So those are the programs that we would normally write as programmers, but we get it wrong. We introduce faults into those. The correct ones are the ones in the middle. The correct ones usually is what we intend to create. But you also know that by testing, this is something that we seldom can prove. Because in order to prove it, we need to test every input. So these are the programs that are correct with every input. The closer you are to the green cloud now, the more correct you are, the fewer bugs you have. So A plus B, perhaps with some error handling for integer overflow, we have the correct solution. For such a toy problem, we can imagine the correct solution. So a test now is like a line over here. This line removes all solutions on the side that is the correct is on one side, and then we have some faulty solutions on the other side. And it removes all those solutions from the possible solution space. So it's a constraint on the solution space. So when we are trying A equals 1 and B equals 1, this one removes the solution with A minus B, the faulty solution, A minus B. So now, with this test case, we cannot have that solution anymore. So we are putting constraints on the solution space. Another test case could put another constraint here. So we are, by putting more test cases, we're closing in on the solution. So some very simple programs like A plus B only needs a few test cases in order to be fully enclosed. More complex programs needs more test cases. And with programs right now, it could be a single method, but it could also be an entire system, right? So we normally try to create some test cases that encloses the system, or the correct version of the system. This line over here is further away from the correct one. And I think I've talked about writing tests that some tests are better than other tests at, closing in the correct solutions. So this test case allows a lot of buggy version, but that may look right. So this test case could be a test case in JavaScript that checks that A plus B is an integer. It just checks type, it doesn't check the value of the return value. So any implementation that returns an integer is a possible solution still. We could also have a test case that this dotted line is further away than the straight line here. So the dotted line test case removes all possible faulty solutions outside here. But this line, the straight line without any dots, is also removing the same faulty versions, which means that the dotted line, we don't need that test case. It's redundant. We should be dry when it comes to our test suite. So if you have two test cases that are testing the same thing, then you should remove one of those. In test-driven development, you do this during the refactor phase. You analyze your test cases. You see that, okay, I cannot find a bug for which this test case is actually needed. So we would like to have as few test cases as possible, because all these test cases is a backpack that you need to carry around. So yeah, okay. So an adequacy criteria could be like this. So a test T for a program P with its requirement R is considered adequate if for each requirement in R, each requirement little r in big R, there is at least one test case in the test suite T that tests the correctness for P with respect to R. Oh, it's a fancy way of getting students confused. But this way of expressing oneself is, a little bit mathematical, or a bit, way of, I'm not sure if you recognize this way or not, but this is the way that we usually try to come up with a very narrow definition of something. But it means like this: if we have a requirement, we have a test case for that requirement. I get a question. During refactoring of the tests, do you use the actual code as test for the refactored tests? The actual code as test for the refactored test. So during refactoring, or after the refactoring, you rerun the test suite that you've written before. So you could keep. There is something called model testing also, and I'm not sure if you're going into that one. If you can clarify your question a little bit, and let's see if we can go further. But this adequacy criteria just means that if we have a requirement, we want at least one test for that requirement. So we have two axes here. So we have requirement output or behavior axis and requirement input domain. And I only have one dot on the input, which means that we only have one test case. So let's imagine that we add another test case over here. That means that we have some other input, we have some other expected output. These are very abstract now, but if you imagine this to be integers, maybe this is the integer where we put in a 0, and this is an integer where we put in 5 or something like that. And then we expect the output to be of some value. But this could be many integers connected, like in the add method, we had 2 integers. So this is the input domain, which is all possible input on this line, and this is the output domain. Now, I don't know. Do you see some pattern between these 2 dots? If you are like me, I would draw a line through them, right? So we see a linear relationship just now through these dots. And if this assumption is correct, in order to test a linear relationship, we would need more than one dot. We would need at least 2 dots in order to see that we have a linear relationship. So if the system is producing linear output, then maybe this is good enough for us in order to cover all possible, remove possible implementation. But let's imagine that we have a nonlinear function like this one. Maybe we would also need another requirement or another test case in order to test that one. Because in this case, we cannot differentiate, with only these 2 test cases, we cannot differentiate between these 2 different methods. So we could have this faulty implementation, but the correct one should be this. And in order to differentiate, or in order to constrain the solution space, we add another test case. Yeah. Okay. So that was the first adequacy criteria. So if you have different requirements, you add test cases so that all requirements are in there. Here we have another adequacy criteria. So a test T for a program P, R is the requirement, is considered adequate if each path in the program is traversed at least once. This is a different way of thinking. So instead, we say that if we go through every part of the use case, or every part of the code, and we have traversed those at least once, then we are okay. So let's think about this code up here. So we have if x is bigger than 2, then we throw an exception. Okay, so you can see if is up here, 2 is down here, and from 2 we don't go anywhere because we have thrown an exception. If we have x less than 2, then we do this do while loop where we increase the x until x is less than until x is less than 2, and then we return x. Not until, while we're doing that. So that means that 1, and then we go to 3 because we never thrown the exception, and then we go into the 4, and we continue to do the 3, 4 until x is while x is less than 2. When it is 2, it's going to return 2 down here. So if we create a graph of the different paths through the code, we can have what I call path coverage. So in order to cover this one, we would need at least one test case that goes 1 to 2, so that this line is covered, and also a test case that goes 1, 3, 4, 3, 4, 5. So we would need 2 test cases in order to path cover this. There is something called loop coverage also. So loop coverage would say that here we have a loop in the program, and we want to go through that loop 0 times, 1 time, and more times in order for it to be covered. So if our coverage criteria is path coverage plus loop coverage, then we would need 1 test case for this one test case for the one where we don't go into in this loop we cannot go 0 times, right? Because it's a do while. So 1 time, so 1, 3, 4, 5, and then 1, 3, 4, 3, 4, 5 in order to loop coverage this. Okay. So how can we know coverage? The tool that, or the most used tool is what's called instrumentation. And instrumentation means that, I didn't have any good examples. Instrumentation means that in order to know coverage of something, we introduce new lines of code into the code. So let's imagine that we want to know if this method is run during tests or not. So, and this is just some system code. It connects to a database. It doesn't matter what it does, because we are only interested in knowing if this is run or not. So let's imagine that we introduce a system out call, or a console log call, or in this case, that we log into some log method where we say that this method has now been called. Then, after running the tests, we can see if we can see do connect in the tests. We could also do a summary where we, analyze the code, we find all the methods in the code, and then we analyze the log and find all the called methods in the log, and we see if there is any mismatch. So are these run or not? So in this case, if I run this one with this log, and I check the log, I have what's called method coverage. Then if I do that with every method, then I have method coverage. I know all the methods that have been run or not. I could also go a step further and see if I add another log line down here. I can also know that I have not only entered the method, I have also exited this method. So I add another log statement before any return statement or when the method ends. And then I know that this one has been fully run. All statements in this one has been run. All programming lines has been run. Because if I connect in during test, if we run this connect line and an exception is thrown, then this is not run. So now I can say that it has been run. It didn't crash. So let's see if I got a question. Yes. Okay, so I got a question before that I didn't fully understand. Let's see if I can understand it. During refactoring of the test, do you use the actual code as test for the refactor test? If tests test the actual code, i.e. the production code under test, when that is tested, can you then use that as a test for the refactored test cases? Use the tested production code regarding that code as an OK, and that way being able to test that the refactored code actually covers all the scenarios the other test cases did. Actually, I'm still not fully onto what you mean, but we could compare to, if we had two models or two different implementations, we can compare these. And if we know that one of the implementation is faulty, then we can compare the test cases that one test suite was better at detecting the faulty ones or not. We're going to go into that one when I'm going to discuss mutation score a bit later in this lecture. Okay, so now from this we can from this we can see if the method was run during tests. We can also see if it's exited during tests. But if we have multiple statements during tests, we could also see introduce one of these do connect, a log line do connect after each statement, and then we can count statements that are run. So let's imagine here we have some code, and here we also have some green and red markings of the code, and this is called line coverage. So this right header code, we can say all lines are green, which means that during tests, at least one test case ran all 3 lines. We can see that the second method, the close method, is not run during tests. So this could be an idea to introduce a new test case for that one. The right body is fully tested, but the right file is not tested. So code coverage is a measurement of how covered the code is. So we can find methods that have not been covered, but we can also find lines of code that has not been covered. So for instance, if we have an if statement, we can see that we did not go into that if statement because the statements inside the if statements are red. Okay, there are many different types of coverage. So we can have different granularities of coverage. So we can say that this component has been used during test, this class has been used during test, this method has been used during test. There's also something called block coverage, which is that if we have a block of code is all statements of the code that is always run together. So let's imagine that you have a couple of lines of code where maybe a equals a plus 1, and then below that is the same statement again, a equals a plus 1. So really we have 2 statements where we just increase a twice, right? These two lines of code is always going to be executed after each other unless we have an integer overflow. So if we remove the idea of an integer overflow, these are always executed together. We can never have any other failure. So I think integer overflows in Java is silent, which means that they always execute together. If I have a statement or an if statement, then we can go into the if statement or we can go to the else part of this if statement. This means that it's a divide. So the if statement is not, if the side inside the if statement is one block, and the part in the else part is another block. So it's going to be divided by that. We could also have statement coverage, is that every part of the code that can be executed individually has its own statement. So I get a question, is there any acceptance level of coverage that is considered good enough? For instance, 75%, 80%, maybe 90%, or is 100% always even possible? So, okay, first, let's imagine that we have 75% of the code covered. There are some code, 25% of the code covered, that is not covered, I mean. Would you go into the back seat of the car? The self-driving car run by that code? Yes. Just to eat pizza there and then go out and not having drive. If it's 100% code coverage, then you would trust it more, right? So when you trust something with your life, you're gonna want higher code coverage, or maybe you want also to know that, okay, we have not had any problems during the last 10 years with this code. So, but if this is a computer game and everyone says that it's fun, it's slightly buggy sometimes, but it's super fun. You must try this one. But you look at its coverage measurement, it says 50%. Would you play the game? It's fun. Come on, don't be such a... It's fun. You can start it. It's okay. It doesn't matter then, right? So the amount of coverage that we consider good enough depends on the case, right? On the specifics of the program. Okay, so we have talked about component, class, method, block, and statement. So component coverage is just that during tests, this component, for instance, this library was used at least in one test case. And class coverage the same. This class has been used during test case. So these are very coarse granularity, right? Doesn't say much about, the specific methods. Okay, we have loop coverage. We already covered that, and path coverage. We also have decision coverage. This means that if we have a decision, then both, and a decision is like an if statement or a control statement where the code is divided into different paths. So a decision coverage means that you are going into the if statement, and you're also not going into the if statement. So I've given you a link to this page. It's a bit old, but most of the theory when it comes to this is very old. So this link will provide you a description of the different types of coverage. So decision coverage reports where the Boolean expression, such as if statement or while statement, are evaluated to both true or false. So what I said, right? But we could have things like this. So you have one condition, and then you have another condition or another condition, and you add this condition with this condition. This is a bit more complex than just going into the if statement or not going into the if statement. And there are reasons for having such, such code. So we need something more. We need what's called multiple condition coverage, which means that if we have a condition like this, we want to, multiple condition means that we want to go into this part of the if statement because this was true. And of course, this is going to needs to be true also because we have an and here. But the reason that we went in that this was true, this or part was true, could either be this one or that one, which means that in order to go into that one and to have multiple condition coverage, you need one test case where this is true and this is true, one test case where this is true and that is true. So you need there are two different test cases going into that one. And then the else part could be many different reasons also. So if this is false, then we go to the else part. But this can also be false, and we should go to the else part. And there could be two different reasons for that. Either this one is false. No, this one needs to be false, and that needs to be false in order to go into that. So you need 4 different test cases to have multiple condition for this one. Not sure if you fully understood what I was saying, but it means that we need to cover all paths, all the reasons that we would go into an if statement and all reasons that we would not go into an if statements. So essentially, you make this truth table, and you do what test cases for covering that truth table. So there is a way of coverage called modified conditioned, MCDC. It's, you can read up on it here. I think that's probably the best. So this type of coverage, where you have multiple decision coverage, is usually it was in the standard for aviation systems. So if you have a program running on an airplane, you would need to cover that in order for it to pass their adequacy criteria. So which is just that we run code. Okay, so if we say 100% coverage is what we intend to have, is that even possible? So let's take a look at a couple of cases where things might not be possible. So I found during my investigations in this that we get sometimes lines of code that cannot be run during a test. So in some version of Java, you couldn't really run the main method because it was static, and then you could not run static code during tests. Sometimes if you have hard-coded, too much hard-coded in your program, then you cannot run the actual program during test because it's going to do stuff. So if you imagine that you are creating a navigation system for a rocket, and everything is hard-coded so that the system, in order to run it, it must be in the rocket. The only way to test it then is to launch the rocket and run the test. So some stuff is not really testable. If we have a criteria that is loop coverage, and that criteria says that a loop must be run 0 times, 1 times, or more times, and then you have a loop that always runs more times. So let's take a look at this header class. So this is part of a web server code. You have an enum, which is an HTTP header with different types of stuff that should be in an HTTP message. And then I have a for loop down here that goes through all those values. Since there are more than 0 values and more than 1 value, I can never get loop coverage for this for loop. It's a feature. It's supposed to be that way, right? So since we are stepping through every one of these, and they can never be 0, they can never be 1, because there are multiple ones, then we can never have loop coverage for this one. So if I have loop coverage as my criteria, I need to write my code in a way that I can replace this enum with something else. Did I make sense? Do you understand why I could not get 100% loop coverage? I only get a 33% loop coverage for this loop because I only cover one of the 3 different things for loop coverage. Some error handling code is also impossible to run, or unreachable coverage. So in this case, the error handling code is probably pretty easy. I just send a string header here with at least 3 parts or 0 parts. When I divide it by a colon, it's going to be divided in many parts, and then I easily can create a test case. But there are ways that you write your code that makes this error can never happen. So you cannot introduce it. Or if you've hard-coded stuff, so that it always needs to run on a specific hardware or so, you might not even be able to cover that code. We could have double checks. So if you're checking the same thing twice, so if you have an if statement checking that A is bigger than 2, and then somewhere inside that if statement, you also again check if a is bigger than 2, and you don't change the value of a anywhere in between, then you have a double check, and then you got also, or if you check that a is less than 2 somewhere, you cannot reach that part, because it's always bigger than 2, because you already checked it in the outer code. Yeah. So there are also some stuff that is harder to test. So if you have resources like a file system, yeah, let's take a break before this one. So we're going to continue with more cases, but the time is 10:10, so let's continue 10 minutes past 10. Let's get some coffee. Okay. Yeah. So we're starting again, and I was talking about different code that could be hard to get coverage for, and it sort of also overlaps to code that is hard to test. So the different experiences that I've had is that if you have a resource, like a file system, for instance, this resource might not be available during tests. So imagine that you run it on your local system, you don't have the, or you need the file system or the folders in the file systems to be set up in the way that the code wants it to be in order to test it on your local system. If you run it on, if you run it in the system's environment where it's supposed to run, maybe you have stuff in the file system that you don't want to risk. So you cannot really run these test cases there. But if you have resources, file system, databases, API, or network, they might be hard to test because they are outside, they require time, you need to configure these, you have hidden dependencies, you have stuff that is hard to test. If you have special hardware, for instance, if you run an Arduino or some kind of microcontroller, it might be hard to test the code that is specifically written for this hardware outside of this hardware. There are usually some kinds of emulators, but it's not always the time that, or always the case that these things work. So for instance, if you're writing I think it's called, like, with a fun name, I've always hated that, cyber physical system, where you have source code running, but you also have hardware connected to that one. So the system is not only source code, it's also, buttons and wires and LED lights that are lighting up and sensors and stuff like that. So maybe that code cannot really run in an automated unit test. It must be run on this specific hardware, and then you cannot, easily check coverage for that one. If you have multiple languages, sometimes in the same file, that is also hard to cover. So you probably encounter regular expressions, and we just put those as strings into our source code. But really, a regular expression is source code. It's a language in itself. It has its own if statements. It has its own branching. And in order to, fully test a regular expression, you would need several test cases. So regular expression probably needs testing outside of your application in order to test that case in really good, right? I've also encountered where we have script languages inside another program. So in computer games, it's quite common that the level developers are scripting their levels. For instance, in the scripting language Lua, but I've also encountered this Lua in home automation. So you could have maybe Java code or JavaScript code, and then inside that code, you have other code, like a regular expression or Lua code. And that code itself is hard to show coverage for. Usually my recommendation would be to separate these out. So the regular expression is tested outside of your code in its own testing environment. And the Lua script is also outside of you, and you import those as files, and then you test that the import is working and that your collaboration with this, it's actually an integration test where your collaboration with the script is working as it should be. But then you can mock the import. Okay, data-driven code. This is almost the same thing as with when you have a regular expression. So sometimes we write code where most of the logic is perhaps in a JSON file or in an XML file. So you configure your program in a very detailed way using data. So you read for instance, in when you write Android application, you are configuring how classes are supposed to be put together using XML, I think. So you're configuring your dependency injection with XML. And this is hard to test because we don't have frameworks for testing that. I don't know if there exist frameworks. So, so if we have very complex input, and that input is, running your code in a way that your code almost is more an interpreter than actual normal code, then that makes your tests that code hard to test. Sometimes if we have iterative or recursive functions, so a recursive function is calling itself many times. An iterative function is run many times, like in a for loop, but maybe it's going to be run thousands of times, and some complex stuff is going to happen. Then we have many, many, many branches, right? So if you're going to have loop coverage or stuff like that, you really need to imagine all these branching, and then on how to go through that. There are also stuff like neural nets, where it's the similar case where we have a lot of data compressed into these neuron weight, and we don't fully understand how that works, or we can only understand a part of it, but it's hard to understand the system as a whole. So it's hard to test this in a good way. So it's hard also to show coverage for. I usually, when people are starting with assignment 1, part 2, also get questions about private methods. So we can have from tests unreachable interfaces, which means that, for instance, you're going to test a class. It has public methods. No problem calling the public methods, but it also has private methods, and we cannot call a private method directly from a test. This means that how should we test the code inside the private methods? There are a couple of different answers to this question. The first one is that you test the private methods through your public methods. So you reach the code inside the private methods by using the public methods as interfaces. That could be difficult if you have a complex system. So it would be nice to be able to replace those private methods during tests, just in order to test the private methods by itself and the public methods where we mock the private method. So in order to do this, my suggestion is to split up the class. It's doing too much. Split it up into 2 different cases. So the case I had in mind when I was doing this, or that I've experienced this particular thing, was that I did a social security number validator. And I realized that in the social security number, we get a string in, and we're going to see, is this really a social security number? Yeah, I hope you understand the problem with this, right? So it is 6 or 8 numbers first, then a minus sign or a plus sign, and then 4 digits again. So what I realized was that the private methods was really working on this numeric string. So it was first a numeric string with 6 or 8 characters, then a plus or minus sign, and then a numerical string again with 4 characters. So by dividing this social security number into a second class, which I call the numerical string, which just checked that all the characters in this was a number between 0 and 9 on all the positions, I could divide it into 2 separate classes, and the numerical string had its methods publicly. But the numerical string could then be dependency injected into the social security number, and voila, I could, replace that troublesome dependency with a mock object and then solve all my testing problems. We can still have stuff that is hard to test or unreachable interfaces, for instance, when we have final classes like the console. In that case, we wrap the console class in our wrapper class, and we provide our own interface, and therefore we can, mock our own class. Okay, more problems. So when investigating, I think this, when investigating different test suites written by other developers, I ran into smoke tests. And smoke tests, you remember smoke testing from the first lecture, was when we try to run as large part of the system as possible and then see if we saw smoke. And smoke could be that the system crashed, or the system ran with 100% CPU, but nothing happens, or that an exception is thrown, right? So a smoke test, when it comes to unit testing, is a test without conditioning asserts. So it only starts up the system, runs system code, and then ends. If there is an exception thrown, fine. That is the usefulness of smoke tests in order to find if exceptions are thrown or error are thrown. However, these become troublesome for us, because if I run the system.run, and then I don't have any asserts, I'm not actually checking that anything, the output. And if I have such a test in my test suite, then it's going to give good coverage because I'm going to run a large part of the code, but it doesn't say anything about the system's functionality or its correctness or its reliability, because nothing's asserted. So any system that runs could be this. And it still runs a lot of code. So when I look at the coverage report, it's going to say, oh, all this code has been run. Looks really, really great, 100% coverage, but nothing was asserted. Would you get into the car? Would you trust that system? So it's not enough to have to just run the code. We also want to check that. We also want to assert that the code did what it's supposed to do. We want to check with the expected output. There are cases where a test case don't need an assert, but is still a valid test case. So imagine the following thing, where we have, so that the source code here is in the Slack conversation. So in this case, I have a die class, so we roll the die. But if I send it a null, so the constructor should throw with no parameter, then it should throw an exception. So if it doesn't throw an exception, I fail it. So by the way, this is a way of testing exceptions if that is not a feature in your testing framework. So you can always have try catch, and you assert if you reach this, assert fail if you reach this line. Everyone understands that test case. So should throw an exception if it throws an exception. Okay, the interesting thing here is now, if I create a random or a die where I don't throw an exception, I should not get an exception thrown. So that test case doesn't really assert anything, because it asserts that I'm not throwing an exception. It is a complementary test case to the first one. It still has value because I know that it doesn't throw an exception if I input the correct things, but nothing more. So this test case down here, it's going to give me a lot of coverage, but unless I have this test case also that it throws an exception when with faulty input, then this coverage is sort of false coverage. So these test cases are connected to each other and only valuable when we have both. Sort of. You see the but the problem is that this one might do, if I have a lot of code in the constructor, then I might also, get coverage for that code. So if I have a lot of code in my constructor, then I also need to do other things with the object, like checking that parameters are set or arguments are set to their values. So that was a complementary negative test. Okay. So now you know a little bit about coverage. So let's imagine that we have good coverage, 100% coverage. Does the system work? Or how good was those test suites? When you were programming in assignment 1, part 1, and hopefully that you've in the middle of that or have already finished assignment 1, part 1, because the deadline is on Wednesday night, the deadline, 23:59, Wednesday night. So everyone should finish. If you have not started, you should start it directly after this lecture. Make sure that you finish it on Wednesday. In assignment 1, part 1, I am testing your ability to write test suites. And I do that by something called mutation testing. Not actually mutation testing, but I'm doing it manually. So mutation testing is to test a test suite. We want to know if the test suite is good at finding faulty implementations or not. We want to assess the test suite. So the first way of assessing test suite is coverage. So does it cover the code? Now we're introducing a new way of doing it. Can it differentiate between a correct version of the system to a faulty version of the system? So let's imagine that we could get a lot of faulty versions of the system, and we would like your test suites to fail each and every version of that is faulty, but it should still pass the correct version. So mutation score does this. So it seeds artificial defects, what we call mutants, into a program, and then checks whether your test suite can find them or not. So if I had the add method and the correct version of the add method with A plus B, we can create a mutant A minus B and a second mutant A times B, or a third mutant return 0 or return A divided by B. All of those are faulty versions of add, right? And then we run the test suite against each and every one of those and see if it fails them. If it fails them, then it's a good test suite. If it doesn't fail them, then we have a problem with our test suite. We should add more test cases. It's not strong enough. So when we add a mutation, then we get something called a mutation score. There is a problem with mutations, and we're going to look at an example in order to understand that. So here we have a piece of code. It should throw exception. Oh, this is the actual tests, right? So input is 5. We call the method. It's called call with this input, and we assert fail here because it should throw an exception. Makes sense? It's the same thing as assert exception, right? So the first implementation is like this. I bigger than 4, then it throws an exception. We create a mutant of that by replacing this one with less than. So I run the test suite on this mutant. Input is 4. Call with input. Okay. So I is the input, 5 less than 4. No, it's not throwing an exception anymore. It's bigger than 4, right? So it's not going to throw an exception. So I'm going to get a fail. So we have catched that mutant. We killed the mutant, it's called. Then I create a new test case here. I bigger or equals to 4. With this test case, 5. Let's check. It's going to throw an exception. So we're actually not finding, with this test case, we're not killing this mutant. The problem is that we are not testing on the edge of this if statement. We're testing with 5 and not with 4. So if I had another test case where we're also testing with 4, then I would kill this mutant. You understand? This one is even harder. So take a look at that code and see if you can come up with a test case that fails that code. The top one, just to remind you, the top one here is the correct implementation. And this one, try to come up with a test case that fails that one. So we just to try it, we input 5. It checks, yes, it's equal to 5, so it's going to throw an exception. So this test case doesn't kill this mutant. Let's input 4 instead, because 4 is going to not throw here, and it should not throw, right? Complementary test case. So we input 4 into this one, doesn't throw. We input 4 into this one, it doesn't throw. So this one, can we kill that mutant? If this is an integer? No. This one and that one are equivalent. For any input, they are doing the same thing. There are 2 correct versions of the system. So we can mutate ourselves to correct versions of the system. Those are called equivalent implementations. They are true. So we cannot, input anything where they are doing anything else than the system is doing. So a problem is that if we're automatically generating mutants, we need this mutant may be actual equivalent implementations. So when I ran mutation score on my own code, I get a mutation score of like 90%. So I'm finding 90% of the mutants. But the 10% that I don't find could either be that I'm missing a test, like up here, right? No, like this one. I'm missing a test. I should test with a 4 also, right? But it could also be that I have an equivalent implementation. So the mutation score here now is just 1 out of 3. 33% of the mutants are found. But this case, I'm having a missing test case, and in this case, I have an okay test suite, but we can't really find this. Okay, so that is mutation score. So mutation score is a good tool, but in order to find out if we need to add more test cases, we need to consider these equivalent implementations. Okay, there is a second way. This is a bit more experimental. So this was done 2013, David Schuler and Andreas Seller. And they were experimenting with something called dynamic slicing. And a dynamic slicer is a way of looking at when a program is run, so it's dynamically run, we can see what lines of code contributed to a certain value in a variable. And this is quite cool, because if you do that, you can look at the values that we are asserting, and then we're looking at the different lines of code that contributed to those values, got to the value they had. So let's look at this do calculate here. So y is our input, and then we go down here, x equals 5. Then we print this value, and then we reduce x with the value that comes in here, and then check something. We assign x the value y, and then we return x. So it's a quite simple function, stupid really. And then we have a test case here down where we call the system under test, do calculate with a 1. We put the result in actual, and then we insert actual equals 4. Okay. We go into this one with a 1 now. X is 5. We print that. X minus 1 if 4. And now y is 1 and x is 4. 1 bigger than x? No, it's not. No, 1 bigger than 4? No, it's not. It's going to return a 4, right? And we assert that those two are equal. However, some lines did not contribute to the result that actual was 4. For instance, this line x equals y, but that line was also not executed in the system under test, executed while we ran it, this particular one, right? So this line we would find in just normal coverage because we didn't go into this one. But this line, the print line, also did not contribute to x being 4. So the print line statement, we get coverage for that one because it's executed, but it didn't contribute in any way to us getting a 4 out of this method, which means that we get sort of false coverage. We would need another test case where we check that x has been printed. Make sense? So dynamic slicing allows us to do this. It sort of keeps different paths through a program and variable values. It takes a shitload time to do this because it's, you know, it's sort of saving every path through the program. This is called a dynamic slice. And you can read about it in their paper. I think I found another more recent paper on it also. No, this was the same thing. So I did some experimentations with this myself, and I found out that where I compared checked coverage with code coverage for, you know, a quite thoroughly written test suite written by me. And then I compared the statement coverage, statement and line coverage. Those are always the same. And then the mutation score, I think that is the red and blue. No, let's see here if I can. The line coverage is the white. The checked coverage is the yellow. And then I think this is a mutation score. And I compare this in different cases. So if we're looking at the graphs down here, we can see it's very seldom that line coverage and checked coverage are not the same. That would mean that we have white, but we don't have yellow. It's quite common. These lines, for instance, are, we don't get any mutation score for these lines because we only run this part of the code. But over, and let's see if we can find over here, we have line coverage, but we don't have checked coverage. However, if we have a mutation, we can find that also. What this really says that if you're constructing your tests in a good way, you are asserting things, and you're trying to reduce the amount of code that is run in each test in order to get good accuracy, then you will also get high checked coverage. So you make sure that you have at least one assert statement for more or less each line of code that you have. So if you're working in a TDD manner, you're going to get high checked coverage. You're going to get a good test suite. Not sure if this made sense to you. It's just based on my own experiments. But I tried to, you know, be very careful when I wrote this test suite, and I found out that I get high coverage, I get 100% coverage, but I also get like 90% checked coverage, and I get a 90% mutation score. So by writing code in TDD manner, you're going to get really good test suites. Okay, so if we read the supplementary course literature, the Kent Beck TDD test-driven development by example, he says that insufficient coverage is a sign of badly designed tests. So if we are running coverage measurement on our test suites and we have not really written tests before we write code, then we're going to have badly designed tests. So I'm just going to show from my own mistakes. So I was preparing for last lecture, and I was writing code in a TDD manner, and I was working in TDD manner. So I was writing code for a Sudoku board just to prepare, right? So I was starting, like I probably showed you, that, okay, this constructor should throw an exception on a null board, and then I sent it a null, and then I created a complementary test case where constructor should not throw an exception for a complete Sudoku, and I introduced that. This was a complementary test, so it didn't assert anything. And then I created constructor should throw exceptions on short arrays. So I created an array that was not 81 long anymore. And then for high values, I put one of the values into a 10 instead of 9 and asserted that it throwed. So, and I do at the same time developed the code like this. This is the constructor. And then I had a private method here that was tested through the public interface of the constructor. It contained a lot of lines of code, as you can see. And I didn't really bother to refactor this code. So I was working with this. So the interesting thing now, did I get good coverage on this code or not? So in order to find that out, I installed and ran jcoco, which is a testing tool. And if we look at the test report, we can find out. So let's do it like this. Oh, revealing File Explorer. Let's open the report. And then let's look at the Sudoku part. And we can set that I got 88% coverage. If we step into that one, we can see that the hint class doesn't really have any lines of code. So, but should throw an exception on duplicates. The constructor is 100% tested. Get position from XY is 100% tested, but get hints is not tested. Let's look at that. We can look at the coverage report for the class, and we can see that by writing the unit test for the constructor the way that I did, I get 100% code coverage for this one. Things looks okay. Now down here in get a push from XY, we get some yellow lines. We can learn that one of 2 branches is missed. This means that I go into the if statement, but I don't never miss the if statement, so to speak. I never go into the else part of it. But when we go down to the end of this, we can see that I have read code. So what happened here? It's actually where I stopped in the end of the programming session, where I tried to get a hint from a Sudoku board. So I was programming and I stopped writing tests because I was, going into problem-solving mode and starting to solve the problem instead of working in TDD manner. So here, the coverage tool can help me to make sure that I'm writing good tested code all the time, but I need to check the coverage reports once in a while in order to find that out. Okay. So where is the lecture? So this one. So I think coverage tools is a really good measure, but what you really need is to write unit tests. And TDD is a good way of writing these unit tests in a way that you get high coverage. There are other ways to assess your test suite, like mutation score, but mutation score had these equivalent mutations, which polluted the score a little bit. And then we have this more experimental checked coverage. I don't know if there is really any tool that is really good for it, where we can find which lines are really asserted. But it takes a lot of time to run these coverage measurements. Okay, so we're going to have 10 minutes break, and then we're going to talk a little bit about the assignments. I have a question also before the break. Do we get online access to Wiley online library through LNU? Yes, you do. So you go to this page. I searched for LNU library plugin. So from the library site, you can download the Lean Library Access plugin, and then you follow the instructions, and then you can get access to a lot of different scientific articles. Yes, it's in, I think this should be in the description of assignment 3. Okay, let's have 10 minutes break. Okay, so we're going to continue with a little bit of talking about the assignments. And I'm going to get some questions on assignment 2. So I'm just going to give you some walkthrough through assignment 2. Okay, so assignment 2 is to conduct testing on an open source project. So I consider this the system testing part of this course. So I would prefer this to be an application to a library. So if Yoda time library, if we're only testing Yoda time library, we're only testing a module, right? We're only testing a library. We're not testing a full application. So we're missing out on the opportunity to conduct like manual test cases, to work with a user interface and stuff like that. So select a project which you would like to learn testing about. So if you're only interested like in unit testing, then Yoda time is good because it has a lot of unit tests. It's very free in its implementation to try find a good project of good size or project which you can divide into manageable pieces to work with. I think one of the biggest problem is that if you select a too small project, then there is nothing to work with. Too little stuff to work with, and then it's not interesting. So the idea or the way that you can get failing this project is, okay, you selected this small Java library or this small JavaScript library, and it only contained 20 tests or so. So you don't have enough information to build the assignment from. Okay, so you can work in groups of 2 or 3, but you must make sure that equal effort is done by each individual. It's your responsibility to divide the work amongst you. You will present your chosen project. And during the presentation, it's going to be an interactive workshop where other students can ask you about your project. So each presentation is not going to be very long. It's like 5 minutes presentation, but you're going to have a discussion afterwards. Okay, the aim is to get you to working with existing programs and testing them in new and interesting ways. So let's talk about what is a good project. So the project must have some form of requirement specification, or that the requirements are easy to interpret from its implementation. This means that you must understand the system in order to test the system. So we must be able to build an understanding of the system. So if this is a very simple system, let's say a web shop, you've all tried hundreds of web shops, so you know how a web shop works. Probably. They can be different, right? So they can have different sizes, implement different requirements. You don't fully understand how this particular web shop works, but you can imagine, you can map it out because you have an understanding of the system. If you are going to work with Yoda time, you probably need to understand a little bit about different calendars. So that there are different calendars to start with, and that they can overlap or have different length and stuff like that, or they start on different dates. There are many different New Years. My brother is celebrating at least 2 New Years every year, right? Because they have 2 different calendars to go through. Okay. It needs to at least have some form of automatic unit testing done. This is the minimum requirement. But the more testing done, the better. The more they document their testing, the better. Don't go for too small projects or too little documentation. It's not going to have enough for you to learn from. It should be a functional capability in prior development. Means that you don't start a new project in assignment 2 and test that. You should learn from someone else, right? We want it to be maintained so that it's somewhat still in use, not being too small. Restrict yourself in size to maintain possible overview of the project's functionality. I mean, there are projects like the Linux. Let's say we test Ubuntu. It's not one program; it's thousands of programs, right? It's super big. So in order to be able to have a slice that we can overview, we need to have that. So, but you could test something specific from Ubuntu, right? Okay, I'm gonna test the scheduler, or I'm gonna, you know, focus on the tests of the scheduler. That is the slice of Ubuntu that I'm doing. Then it must be executable and functional for you. So one tip here is that if you can today download an installable version, or you install the version on your machine and run their installable version, then that's a good project. So for instance, Google Authenticator is one of the projects. I have it installed on my phone using the regular app store, and then I can test it using the regular App Store version, right? Since I have it executable and runnable function for me. Okay, so you should be able to run the existing test. This means that you need to install the frameworks, you need to set up Gradle or Maven or whatever tools that they use to run their tests. You need to understand their purpose and fundamentality. This means that if you don't understand what they write, if you're selecting something written in a completely different programming language than you've ever experienced, you might not be able to fulfill this. So my suggestion is at least take Java or JavaScript, or something that you've encountered before that allows you to read the code and understand the code. And if you've been working with Gradle and they are using Ant, maybe it's better to take a Gradle project, unless they have good implementation and how to get their tests started, or you are a problem solver. So I would early on make sure that each of these requirements are fulfilled, that you're able to run the tests. So if you need to spend more than 2 hours just getting the test suites running, then probably step away from that project, select another one. You should run the existing test, and this could also be the manual test, right? So if you have an executable functional version of the software, then you can run the manual tests on this software. You should be able to provide the results of existing tests. So if you run the tests and they show that there are bugs, you should be able to explain what the tests do, what kind of problems they solve, how they fulfill the requirements, or how they overlap the requirements. And you should be able to perform exploratory testing on the project. So exploratory testing is covered during the external resource here. And this video by James Buck, I strongly recommend you to look at that video before starting. You can see that it's a bit old video, but I think it's fun. He says that there is no test education anywhere at the university level that is of any value. So, which I think is a good challenge. Yeah. Okay, and then we have some requirements, and the mandatory requirements is for E grade, so to speak. You should be able to shortly describe the project. What is its purpose? What does it aim to accomplish? Provide an overview of the requirements and specifications, stakeholders, risk, and evaluations, stuff like that. There might not be information on everything in every project. But and then it says the past, present, and future development of the project. And yeah, so all of this is actually just to understand what kind of project are we looking at, so that you understand why are they testing, the test goals of this project. We have not started with system testing yet during the lectures, so I hope this is going to be more clear in the future lectures. But if we understand the situation of that project, like, for instance, we are testing a self-driving car, that is different from a computer game, because we have different things at stake, right? Different purposes. Driving the tests of these two projects in different ways, right? Okay, then we go into what they have provided on their tests. So their current test strategy, there are kinds of tests being performed and how the tests are reported on. So if you're interested in going ahead, you can listen to the previous year's lecture on system testing and, you know, going into these things already. What tools are used? How do they handle bugs? And then you do testing. You run their tests and you do their manual tests and you run their automatic test suites and you document doing that. So you do, yeah. So what did you do and what did you find? How many bugs did you encounter? What test cases failed or no test case failed? What kind of coverage do they have? You document the pre-existing tests and the results. Okay. So I might have mentioned coverage. I should not have done that. So for higher grade now, for D2A, give judgment on the quality of tests. That was this lecture's content, right? So what coverage do they have? Do they have a process where this is a part of? We could see in the Yoda time you need it in order to have a pull request. You needed to provide coverage measurement inside that one, right? So they can see that the code that you provided is covered by test. How far have they gone with automation of this project? So this is also a quality statement of the project's testing. If it's fully automated, it's higher quality than if it contains a lot of manual steps. Because manual steps takes time. Manual steps are boring. We frequently make mistakes when we're testing manually. Do they achieve their purpose and make sure that the program is stable? And then, so you give judgment of the quality of the tests, and then you suggest improvement for testing. Motivating why? So let's say that you find that they only have 60% coverage. So your suggestion for improvement is adding new test cases. Motivating why, yes, this part of the code probably needs more test cases because it seems to be important. Or justify why the current test effort is sufficient. So some of these projects might be really, really good at their testing effort. And then you say that, okay, this is good enough for this purpose. This is a self-driving car, but they have a super good test suite, so I'm getting in the back seat of this car. I'm okay with this. This is good enough. You find out, are there missing tests? Can tests be automated? Yeah. And finally, more or less, not finally, you also need to write improved tests. So you add to their test suite. Motivate the reason for inclusion of these tests. If you perform different kinds of tests, document and motivate why. Why couldn't you include some form of testing? So you could also come up with the case where this was not possible to include new tests for this part. So you may sort of fail, but you have reasons for your failure. But this is quite interesting and hopefully also useful for you and for the project that you create new tests for this. So let's imagine that they have bad coverage, like 75% coverage, and you increase their coverage to 80%. That is a 5% contribution to their test effort. Of course, try to do contact these developers or, you know, give them your tests also. So yeah. Perform more than functional testing. So you know that there are functional requirements and non-functional requirements. Non-functional requirements are usually these more fuzzy requirements, like the system should be responsive, for instance. So maybe we can test the system's responsiveness. Maybe we do some load testing of the system. So we set up a server, we set up so that we load test it with 100 requests every second or something like that, and then we have responsiveness testing at the same time or something like that. Could also be accessibility testing for, you know, disability or things like that. So there are these checklists or automated tools also where you can run on a web application, for instance, and make sure that it's accessible for people with disabilities. Yes, discover and discuss new scenarios for exploratory testing to perform. Yeah, again, with exploratory testing, check the lecture by James Bach. And then what's the reliability and scalability of the project? Is the project secure and unsafe? Who can use it? And how is it accessible enough? So the entire idea with this entire thing is that for E grade, you investigate what is there. For higher grade, you try to improve their testing, right? It's super open, this one. This makes it hard, because you are used to very closed assignments, I'm assuming, where, you know, do this, then that. I want you to go from the student who jumped when I say jump to the student who thinks for themselves. I want you to focus on your learning effort. I want you to think about, okay, what do I want to learn about system testing, and then make sure to learn that thing. I want you to think about, okay, this project doesn't have any manual test cases. What would be good manual test cases to include this? How can we contribute to this project's testing? How would we write a manual test case for this thing? The deadline for submission is in January, and you're going to have a presentation workshop. It should be in the schedule right now. I'm not sure that this is correct. That's probably last year. And I have some examples of open source projects. I cannot guarantee that these projects are good ones anymore, because many of those changed. So I looked at Google Authenticator. I found out that it has moved and stuff like that. So so some things go deprecated, some things go old. Find something cool. I would suggest test an open source tool that you're already using. Questions? We're going to talk more about system testing. Next week. So I'm gonna give you more about that. So hopefully we can make things a little bit more clear on what you can include in system testing next week. Questions? Did I cover everything that you needed? Yeah. Okay, assignment 1, part 2. I strongly suggest that you take a look at the TDD guide. This was lectures that I have recorded previously. I also suggest that you read the TDD book in order to do that, and also that you stick with the TDD assignment. So I've talked a little bit about this during the last lecture, but we can quickly go through it. It's a single or pairwise student assignment. I suggest to pair up with someone and do what I call test pong. So single student or a maximum of 2 students. The examination is still individual. It's going to be oral examination. Yeah, it is an optional assignment for higher grades. So you can still, if you passed assignment 1, part 1, you have an E. I'm not going to remove that from you. The worst case is that you still have an E when you know went from the examination. That has not happened yet. So the lowest grade I've given for assignment 1, part 2 is a D. So yeah, so you decide the language of implementation. So you can have Java, don't need to be PHP. You decide a framework for unit testing. It could be JUnit 4 or 5 or something like that. A framework for mocking, like Mockito. A code coverage tool, code cover, or Yokomoko, or whatever it was called, Yokoko. In some cases, all of these are in the same framework. So it doesn't need to be separate frameworks. You decide what sort of project you're going to do, like a dice game or something like that. There are some minimum requirements. The first one is that you have a Git commit history. The Git commits is usually, I say, at least 20 commits. Usually for higher grades, there are hundreds of commits, like a couple of hundreds. 300s is quite common, 200 commits. Since you're committing so often, these numbers go up very well, right? So the first commit you do after you write the test, then you write red in your commit message, and green, you write green in your commit message, and refactor, you write refactor. At some point, you do coverage measurement, and then you write coverage when you include that report in your commit history. And during the examination, I'm going to ask you, show me a red-green refactor cycle where you that you think represents TDD in a good way. And then you can, go through your commit history and find these. The size and complexity of the program, it's going to be a quite small program. The important thing here is not that you should choose some impressive implementation with loads of features, but rather that you understand the TDD properly. So this is an exercise. The system itself that you're building is not that important as you learning a shitload of testing. So at least 4 different system classes with dependencies. They need to depend upon each other, right? Final project. The more classes, the better. Use dependency injection. You need to mock and isolate dependencies. Somewhere in your program, you need to use dynamic object creation. This is just what I mean, that you create objects like new. So this needs to happen not only in the constructor or in the initial, main method, but also inside the program. So you're calling a method and an object is created somewhere. This is just to encounter the situation where, which is difficult to test, which is that we have new somewhere with a class name somewhere in our program. And this can be solved by factories pattern, and then you mock these factories. You need to understand TDD, unit testing, mocking, and coverage. Yeah. And it's going to be individual examination. You're going to show your programming environment with almost 100% unit test coverage. 100% is the goal, sometimes not possible. You show your commit history. The longer history, the better. Show how mocking is used. Show that you can find code not covered by any test, by code coverage. Show source code for classes. And then I have a number of different questions. So go through this when you've done the assignment. Go through this with your partner. And then, so the answer today is, can we always have 100% code coverage? No, we might encounter situations where this is not possible. Depends on the language, depends on how the system code was written, yada yada. You're gonna register for examination by booking an examination. You can click on this booking form. I'm not gonna open it here because it contains names of students. Yeah. And then some on the grade. Okay, I got a question. Do you recommend going through the pyramid you showed at the start of this lecture in the beginning of assignment 1, part 2? I think that when you're working with this assignment, try to, in the beginning, keep it super simple. So you might even do some practices where you do have methods that return something, so that you can write really simple tests for those, like the math tests. Doesn't really need to be a part of the project anymore. But if you decide that I'm going to write a little tic-tac-toe game, and my first test is going to be, and you don't know, it's going to be hard, right? But if you know that, okay, the tic-tac-toe, a level of tic-tac-toe really has 9 different places to place this in. So tic-tac-toe level, and then you have some state inside of that, and then maybe you try to assign a position to one part of that, and you have a set with a value and a position index, and then you can start writing unit testing simple, because you can set a position outside on position 10, something like that, should throw an exception. So start assignment 1, part 2 should be started by coding and not by a long design time. So write a simple test, write a simple implementation. Start by just getting the tools working. More questions? Okay, thank you very much. Thanks for this lecture, and thanks for listening. This might be a lecture you need to repeat a couple of times for the exam in the end.